Kia ora and welcome to this video on question 2 of the 2018 School Calc exam. Okay, so the first part there is a pretty random function, and they ask us about where the function is discontinuous, and then asks us for a limit. Second problem is also a graphs question about perpendicular tangents, and then the third problem is an optimisation question, which we'll look at using two different methods. Alrighty, question 2a is an examiner troll question, which we've seen a few of in the sequence of videos that I've recorded so far, in the sense that if you put these fractions back together, it's just going to be so tedious, lots of algebraic simplification, and actually really unnecessary. The question's asking us values where the function is discontinuous. So that's like, what values of x can we not substitute into this function? So, in other words, discontinuous where f is undefined. Now it might be that there's a hole in the graph, or it could be that there's an asymptote. So there's different types of discontinuities. We can have ones where, like, you might have a normal function but then might have a hole at a particular point. You might have a function that changes its behavior, so a piecewise function, or you could have a function that has an asymptote. So there are different types of discontinuities. So if we make the denominator equal to 0 for this function, so x equals minus 2/3 is going to make that left fraction undefined. X equals 3/5 will make the first fraction undefined as well, or x squared minus 5x plus 3, if that equals 0, and the values of x of where that equals 0 is 5 plus or minus root 13 all over 2. Those are the four values of x that don't work, and therefore there's no y value for them. Every other x value will work because the function's just made up of polynomials. Okay, so they're the values of x where the function is discontinuous. And the second part asks us for this limit, and we're approaching a half. So we're saying as x approaches 1/2, what is the function value approaching? And because it's not one of the values of x that we've ruled out, it must be the function actually must be continuous at x equals 1/2. So we could say the limit, turns out it's minus 8 over 21. We'd say this is the function value, f of 1/2, because the graph is defined and continuous. There. Okay, so if we just have a look at that function, I've prepared it earlier because it took a little bit to type in, but we can see that there's asymptotes at x equals minus 2/3. Okay, that's the asymptote there, so that value of x doesn't work. There's an asymptote at x equals 3/5. And then there's also, it's kind of hard to tell, but if we put in the other ones, what was it, 5 plus root 13 all over 2. There. Oh, there's another one. And 5 minus root 13 over 2 is the one that's really, really close. Oh, look at that. The function's doing some really strange stuff in there. Okay, so they're all asymptotes. And then the limit value, where is the function heading as x goes to 1/2? So if I go and type in x equals 1/2. See the graph there, minus 0.381 is negative 8/21, and the function is heading towards the function value at that point. When you get holes in the graph would be if there's a common factor top and bottom, and if you looked at the function that we were given, the top and bottom didn't share any common factors. So suppose up here, suppose that was like 3x plus 2 times x minus 1, for example. The 3x plus 2 term would cancel top and bottom. It's still a value of x that's not allowed though, so minus 2/3 wouldn't be allowed, but you would just get a hole at that point as opposed to an asymptote. Alrighty, second question. Show that the graphs xy equals √2 and x squared minus y squared equals 1 have perpendicular tangents at their points of intersection. Now the cool thing about this problem is we don't need to find the point of intersection at all. Okay, the question is just asking us to prove a property of their gradients, and it doesn't matter about the point of intersection. We don't need to go find it. But if you did, you would be solving a simultaneous equation. Okay, so perpendicular tangents. Let's actually bring up the how about we bring up the function and have a look at it first. So we've got up two types of hyperbola. Xy equals √2 is a rectangular hyperbola, and then we've got x squared minus y squared equals 1, and I need to zoom this square so that we can actually, is it zoom square? Yeah, I can see that 90-degree point of intersection. Okay, so if we just call this point of intersection P, it doesn't matter that it's actually √2, 1 and minus √2, minus 1 on the other side. But if we just call that point P, suppose they intersect at P, and we'll give that a coordinate A, B, just so that we distinguish between what x and y are as a general points on the curve, and then A, B is a particular point. We just need to prove that the tangents are negative reciprocals, the gradients are negative reciprocals. So, okay, the first equation 1, we can write it as √2 over x, which is the same as √2x to the minus 1, and then dy dx is equal to minus √2 over x squared. And then equation 2, we use implicit differentiation for that one. So we've got 2x minus 2y dy dx equals 0. Therefore dy dx is equal to x over y. And then if we multiply these gradients together, we should get -1 at the point of intersection. So multiplying gradient functions, I'm going to switch out x and y to be a and b now. So I've got -√2 over a squared multiplied by a over b. They are the gradients at the point of intersection. And then this simplifies to -√2 over AB. And we know that at the point AB is on the curve. So we know that A times B must be equal √2, because that's the equation of the first hyperbola. So we've got -√2 over √2, which equals -1. We've proven it. We didn't need to find what A and B were. We just needed to know that AB was a point on the curve. Okay, third question. A roading system is to be designed with 3 towns connected. The towns form an isosceles triangle. How convenient. AB equals AC equals 50. So we've got careful here. AB is equal to 50. AC is equal to 50. And then BC is equal to 60. Use calculus to find the location of D that gives the minimum total length of roading. Show that the length is 40 plus 30 root 3. So D is the thing that can be moved. So if I call this X, we're saying X can range between 0 and 40. And the reason it's 40 is if I make a right angle triangle here, this length will be 30. And it's a 3, 4, 5 triangle, so the biggest value will be 40, and therefore this length in here is 40 minus x. So x can range between 0 and 40, and as it does, we're looking at how long the road becomes. So our function, our length of roading there's 3 roads in there, right? There's the x one, and then there's 2 lots of the diagonal. So we've got L equals x plus 2 lots of the diagonal, which is square root of 30 squared plus 40 minus x all squared. Okay, and we want to differentiate this. So 1. We've got 2 to the 2 multiplied by something to the half, so the half will come down the front. We've got 2 times a half times everything to the power of negative 1/2, which will be same as on the denominator, square root, and then we need to times by the inner function differentiated, which is the 30 squared disappears, and we get 2 lots of 40 minus x times negative 1. Okay, I just didn't want to expand out that stuff underneath, and I just used the chain rule for it. The 2's cancel there. 1, the right factor, this factor in here, is going to be 2 times x minus 40, so 2x minus 80. All over this thing square rooted. Again, we're going to make that equal to 0 to find the minimum road required. So we're solving this equation. 1 equals 80 minus 2x all over this thing. So I've moved it to the other side of the equation, so that's why it's 80 minus 2x. Then I'll cross multiplying, and I'll square as well. $80 minus 2x is the same as 2 lots of 40 minus x, and then I'm squaring that, square and square. Okay, so now we've got a quadratic equation. We've got 900 plus 1600 minus 80x plus x squared, and on the other side we've got 4 times by 40 squared minus 80x times 4, and then plus 4x squared, and if we make it equal to 0, we've got 3x squared minus 320 plus 80, and 6,400 minus 1600 minus 900. Alrighty, if I solve that polynomial, I need to find the exact values, but if I just check these on the polynomial solver, okay, 57.32 or 22.68. 22.68, does that sound right? Oh no, there must be a mistake somewhere. Where is the mistake? I just checked the answer and it wasn't the same. Must be a little mistake on my differentiating or my solving. Oh, actually, I think I know. The NZQA answer has a different thing for x in their diagram. So I'm getting an answer of 22.68. But if I take 40 minus 22.68, no, there's no issues at all. Brilliant. Okay, we continue. The question asks us, show that the length, so find the location and then show that this length is 40 plus 30 root 3. So we're solving this quadratic equation, 240 plus or minus 240 squared minus 4 times 3 times 3,900, big numbers, over 6. 40 plus or minus, now that thing under the square root does simplify, 240 squared minus 12 times 3900 is 10,800, and that's all over 6. And 10,800 has some square factors to it. We can divide it by 64, I think. Nope. We can divide it by 36. Yep, if we divide it by 36, then we can pull the 6 out the front of it, so we end up getting 40 plus or minus root 300. And we can also pull out a factor of 100 there, so 40 plus or minus 10 root 3. The NZQA answer has 10 root 3 as the answer, but they have their x in the diagram. They put their x on the other side, they put it here, which kind of makes the problem a little bit easier because the right angle triangle stuff is easier. We're just going x squared plus 30 squared rather than 40 minus x all squared. Now the length of road for this, it has to be a positive root. No, it has to be the negative root because we said that x had to be between 0 and 40, so it's a negative root to make sure that it doesn't go up beyond 40. And then we want the length of road by substituting in, so we've got 40 minus 10 root 3. I'm subbing way back into my first length equation, plus 2 lots of square root 30 squared plus 40 minus x all squared. And 40 minus x is going to be 10 root 3 all squared. Okay, and if I work out that stuff under the square root again, bear in mind that this problem here, you'd have about 20 minutes to do it in the exam. It's quite a big problem. comes out to be 1200. So 40 minus 10 root 3 plus 2 square root 1200. And we can pull out a factor of 400 out of that. 400, square root of 420. Pull that out with the 2, so we've got 40 minus 10 root 3 plus 40 root 3. And then the root 3's simplify to 40 plus 30 root 3. And that's the length of roading that we were asked to prove. Yep, and then show that it's indeed a minimum. Oh my goodness. So we need a derivative test for this. We can use the first derivative test or the second derivative test. I think because the first derivative is already quite a messy expression, differentiating it again is going to be real tedious. So if we just set up a table, and we know at our stationary point, the value of x was 40 minus 10 root 3. Which is 22.679. So if I pick x equals 22 and x equals 23, and I put it into the derivative, which simplified to this dude. Okay, so L dash. Okay, if I just do that, 1 plus, I'm going to make x 22. Using the table function on the calculator is quite nice, or even just a graph, because we want repeated substitutions. So I do it in the table function, and then I just change the value of x. I don't have to type out the whole formula again. Okay, and then x equals 22 gives me minus 0.028. Just testing, x equals 40 minus 10 root 3 should give me 0. Does, and then 23 gives me 0.0139. So we're saying that the length equation, graph, L versus X, is going downwards, then it's dropping out at a minimum, and then it's going upwards in terms of slope. So that's enough to prove that it's a minimum. Therefore, the point is a min. Alrighty. I did say that we'd look at this in a different way. So if we start off with a diagram again, but this time if I call this angle here theta and use trigonometry, so that's going to be my variable instead. It turns out quite a tidy solution. So let's have a look. If I got the length will be, do I want that to be theta, or can I choose a different positioning? I'm going to choose a different positioning just because of what I learned from that last solution, that if I had made that x there, it would have been a lot tidier. So I'm going to make this angle here theta, and then this side here y. Got cos theta equals 30 over y. So y is 30 over cos theta, which we know is 30 sec theta. And then this value here, x, that's tan of theta equals x over 30. So x is 30 tan theta. And then my length of roading is 2 lots of y, so 60 sec theta, and then 40 minus 30 tan theta. And bearing in mind that we've already talked about y, that's 40 minus x. That's we use Pythagoras on the right angle triangle. Okay, so that's our length formula, and we need to differentiate it. 60 sec theta plus 40 minus 30 tan theta. Okay, so the function itself took a little bit more thinking to build it up. The differentiation is going to be a lot tidier. Sec theta differentiates to sec tan, so 60 sec theta tan theta, 40 disappears, and 30 tan theta differentiates to 30 sec squared theta, and that equals 0. You can divide everything through by 30, and we can also divide by sec theta, because sec theta is never 0. Sec theta doesn't equal 0, so we divide out that stuff, and we end up with 2 tan theta minus sec theta equals 0, or 2 tan theta equals 1 over cos theta. Tan is sine over cos. Cos theta won't be 0 for this problem, because that would give us an angle of 90 degrees, and it's clearly not 90 from the diagram. It just wouldn't make sense if it was 90. The roads wouldn't be. So if theta was 90 degrees, then the road CD would be heading off in that direction, which doesn't make sense. So therefore we're solving 2 sine theta equals 1, sine theta equals a half, sine theta equals a half. The solution to that is 30 degrees. Very, very nice solution. And then we had to find the length of roading. Okay, so that was 60 sec theta. 60 sec theta, which is 60 over cosine theta, plus 40 minus 30 tan theta. We've actually got a triangle here. Whenever we've got a trig ratio, we can get all the rest of them from a triangle. Sine theta equals 1/2 tells us that the opposite side's 1 and the hypotenuse is 2, or some multiple of that. And then that side would be root 3 by Pythagoras. And so cos theta is root 3 over 2. So we've got 60 over root 3 over 2 plus 40, and then tan theta is 1 over root 3. So we've got 120 over root 3 plus 40 minus 30 over root 3, which is 90 over root 3, 40 plus 90 over root 3, and then if we times by root 3 over root 3, the denominator becomes 3, so we get 90 over 3 is 30, so 40 plus 30 root 3, and that's the proof as it was before. Derivative test, we could do the same thing as before and use the first derivative test, or I could do the second derivative because it's actually not that bad. D squared L over D theta squared. We've got to diff the sec tan. I use the product rule for that. Sec differentiates to sec tan, so we've got 60 times sec theta tan theta times tan theta, and then the derivative of tan is sec squared, so sec squared theta times sec theta. Okay, maybe it was a little bit tedious. And then the second part of it's 30 sec squared theta, which is sec theta all squared. So differentiating that, we get minus 60 sec theta to the power of 1 times sec theta differentiated, which is sec theta tan theta. Got 60 sec theta tan squared plus sec cubed minus sec squared tan, and then we need to sub in sine theta equals a half, or we know sine theta equals a half in there, so we need to work out the sec, the tan, and etc. etc. And then decide on whether it's positive or negative. we're using the second derivative test at this value of theta, we want it a minimum, so it'll be concave up, so we want to prove that this second derivative is positive, but I'll leave that for you to do as an exercise. Catch you in the next video.